Good morning class, my name is Mukhtar Patel. Today we are going to discuss object-oriented programming, OOP for short, its concepts and definitions. We are going to learn the principles of OOP. By the end of this lecture you should be able to understand the types of languages and where OOP fits in, understand what classes are and what objects are, be able to identify them in the real world, understand object attributes and methods, and finally understand the three pillars of OOP, which are inheritance, encapsulation and polymorphism. Programming languages. What are programming languages? They allow programmers to create software which simply are instructions for the computer to execute. There are hundreds of languages in existence today, and they can be grouped into one of three categories: machine, assembly and high level. Machine languages are comprised of ones and zeros, which is the native language of a processor. It's pretty clear it would be quite difficult to create software using this language, if not impossible. One misplaced one or a zero will cause the software to malfunction. Software written in machine language would be executed as is. It does not require any kind of translation or processing. This is an example of what machine code would look like, just ones and zeros. Next type is the assembly language. They look similar to machine language, the fundamental difference being the instructions are given names as opposed to merely consisting of numbers, and also clear instructions are used. The CPU will not understand software written in assembly language as before, as the machine language is recognized. The code will require to be translated to machine language first before it can be executed with the processor. It is machine dependent. When writing a software, it is targeted to a specific CPU architecture and specifically written to be executed by that CPU. Almost all operating systems such as Windows, iOS, Android contain approximately 2 to 5% of software written in assembly for critical sections such as the boot code. An example of an assembly language would look like this. As you can see, it is in a readable format. The final type are high-level languages. They are much more English-like in comparison to assembly. A novice developer would understand the functionality of a piece of code by reading it. This example shows a command to create a string representation of an employee. There is an extensive collection of high-level languages developed since the early 80s. They are grouped into either procedural or object-oriented languages. Procedural languages rely on well-formed structures containing routines, which are a series of actions to be carried out. Examples of procedural languages are fairly old, such as C, Visual, Basic, etc. Before the program can be executed, it needs to be translated to a machine language by a tool known as a compiler. Now, in comparison to object-oriented languages, which focus on the model rather than the structure that exists, they interact with one another as well. Some languages simply tell the computer to do this or do that, whereas do it differently. They focus on organizing data into distinct packages known as objects. They are able to perform certain tasks. These objects are able to interact with one another in an organized fashion to solve complex problems in an easy to understand manner. The objects are reusable, versatile, and they model real-world items. As before, the software must be translated to machine code before it can be executed. This process is much more complicated due to complex relationships the objects can have with one another. An example of an object-oriented language is Java, C#, C++, etc. Moving on to the definitions now. A class. A class is a blueprint which defines the properties and operations of an object. It defines what the object will be, what the object's characteristics are, and a key fact to remember is many objects can be created from one class in the same manner many photos can be developed from one blueprint. Programming languages come shipped with a library of classes which allow the developer to create software. This availability enables the developer to reuse them and create their own classes, which again can be reused. Next are the objects. Objects mimic real-world items such as cars, trains, people, etc. Objects and classes go hand in hand. A class is used to create an object, which is also referred to as an instance of the class. The process of creating the object is known as instantiation. An object by definition is a software bundle of states and behaviors, usually modeling real-world items. But what does that really mean? Let's take a bicycle as an example. Firstly, a blueprint will be needed of a bicycle that defines all its characteristics and behaviors. Now, using this blueprint, many objects can be constructed. The objects are used to show how a bicycle is, its characteristics, what it can do, who or what it interacts with, what it depends on. In the world of software, they work similarly to how real-world objects do. Objects have states, which is the description of the object, which are stored in fields that are specific to a class. They also have behaviors, which are captured in methods, which is what the object can do. The methods contain actual code that tell the computer what to do. If we look at the bike, it has color, type, manufacturer, model, gear count, and if it's in motion, it will have speed, current gear, rider, etc. The behaviors the bike can implement are pedaling, braking, turning, changing gears, or any other function the bike can perform. Now let's consider a rock. What characteristics will a rock have? A rock will have a position, XY coordinates. It'll have state. Is it wet, dry, hot? All these conditions need to be considered when mapping real-world items to software. Now, next item is encapsulation. A simple way to understand encapsulation is to assume object properties reside in the center and the methods surround them to keep them safe away from other objects. Not all properties need to be hidden. Some may need to be exposed to allow this object to communicate with others through getter and setter operations. All methods, the state of an object, can be changed or accessed. And it's also how objects communicate with one another. As the name implies, the getters return the values of an object property, which is also referred to as fields, while setters allow the properties to be changed. Requiring all the actions on an object to be done through methods is data encapsulation. Data encapsulation is a feature which allows developers to restrict access to object states and behaviors between classes. This is a very useful feature to have. Let's take a water jug for example. A user object can invoke the appropriate public method on the jug object to add water. However, the method will have the necessary safety checks in place to ensure only a certain amount of water is added. This method ensures more water than what the jug can hold is not added. Why is this a core feature of OOP? If we go back to the jug again, let's say for example the jug has a property which defines the maximum amount of water the jug can hold. This is defined by the programmer using data encapsulation. Using encapsulation, the developer can ensure this property is not visible from the outside world, hence prohibiting access to it and subsequently altering it, which could end up with a wet floor. Moving on to inheritance. Why are classes and objects so important to object-oriented programming? How versatile do they make programs? It used to be the case that a single program would serve a single function, and if you needed to create the same program with little changes, you would need to make another whole program. With the introduction of OOP, the developer can simply tell the class to make the same thing with slightly different attributes. If we take the example of building a house, it takes an awful lot of time to create a completely new blueprint for a second house, when the only difference between the two houses is that one has a garage or a chimney or neither. Not very efficient. Creating duplicate blueprints can be avoided by using inheritance. Using inheritance, a class is created which defines a blueprint for a basic house. This blueprint is referred to as a parent class or a superclass. Now, the next class which defines the blueprint for a house with a garage will be derived by absorbing the characteristics of the superclass, followed by adding unique characteristics of its own. The whole idea here is saving time, feature maintenance, speedy enhancements, and all of this essentially boils down to saving money. Abstract classes. What are they? Programmers can implement a special type of superclass called abstract class. It is used to define generic behaviors which is either partially implemented or not at all. In specialized subclasses of this abstract class, programmers will fill in the blanks. The abstract class by definition is one that is not intended to be instantiated into an object. It is an incomplete blueprint. The idea is that the subclasses will add the missing details in a way that's specific to that particular implementation. Without abstract classes, you would have to provide dummy implementations of the methods you intend to override, which could be done, but then there'd be the risk of forgetting to implement one of them. Having some methods remain entirely abstract ensures that real implementations have to fill in the gaps, or continue to be abstract themselves and force their descendants to do so. It's not something a language could live without, but it's very useful. You'll discover just how useful as you become more proficient in object-oriented design. The final concept of OOP is polymorphism. Polymorphism is the ability to assign a different meaning or usage to an object in different contexts. More specifically, it is to allow an object to take on more than one form. A classic example is of an animal. If we focus on the eating behavior, we know each animal eats differently. A house cat will eat from its feeding bowl, whereas a giraffe will help itself to nearby trees. Both of these animals eat in a different manner. If we are characterizing this into classes, we would have a superclass called animal containing common characteristics. Because each animal has its own method of munching, it would be a good idea to ensure, well, first to create subclasses for the cat and giraffe, and to ensure that each subclass of the animal is enforced to provide this information. This will be achieved by declaring the eat method abstract. Because we know the cat or giraffe is derived from animal, we also know they must have provided their own implementation of how they eat. Hence, if an object is instantiated for a cat or a giraffe, the developer does not need to know which type of animal it is. All he or she is concerned with is that it's an animal object, and as per its contract, it must have its own implementation of eat. Hence, when the developer invokes eat, depending on which animal it is, the appropriate eat will be executed. This is referred to as polymorphism, probably the most important feature of OOP. Now, to summarize, this ends our short intro on OOP. To sum up today, we have discussed the types of languages available and why OOL have been such a huge success in industry. We know the key characteristics of OOL and its benefits. Moving forward, next week we will develop a small software using object-oriented language, and if you get some time, please do read the notes provided to get a head start. If you have any questions, please do get in touch with me, and if not, I'll see you all next week. Thank you. Bye.